All right, this is day 2 of chapter 16, where we look at a couple of other important things before we put a close to this chapter and move on to kinetics. Some things we'll be talking about today. I figure since all these lectures are on video, I don't need to spend time doing review because you could always just go back to earlier videos to review what I talked about then. So we're going to jump straight into gas effusion. And then we'll take a more detailed look at microscopic molecular collisions, because to this point so far, when thinking about ideal gases, we've assumed that the particles are not colliding with each other. Now we're actually going to start thinking about that. And then we'll end with the concept of the mean free path. Okay, so the first situation that we're going to consider is the phenomenon of effusion. And what effusion is there's a system, a closed container with a small hole that's punctured in the side of it. And inside the container are a number of gas particles all scattered about far away from one another. In fact, they are so far away that their distance from each other is large compared to the size of the hole that's been punctured in the side of the wall. And so we need to ask, for a given pressure, temperature, and other information like mass of the particles, etc., how much gas is going to be flowing out of that hole per amount of time, okay? So in order to calculate this, we first need to calculate a quantity, ZC, which is known as the collisional flux. And what this represents is how many particles are hitting the wall, an area of the wall. It's the number of particles per area per time that are hitting the walls of the container. And once we calculate this, we'll be able to figure out how much is flowing out of that little hole there. So the ZC, the book will tell you, happens to equal P times Avogadro's number divided by 2 pi mRT to the 1/2 power. And again, watch out, this M needs to be in kilograms per mole. All right. There is another equation that it gives you where it's just P, and on the denominator is 2 pi little m kBT to the 1/2 power. Now this m here is the mass of one particle. And again, it's still in kilograms. So it's going to be a very small number. And the reason why these two are equal is because there's a factor of Avogadro's number in both the R and the big M compared to the KB and the little m. So you may have to end up using a formula of this sort where you're using little m instead of big M. The way the book presents effusion itself is there's going to be a change in pressure with respect to time as the gas flows out. And the book defines this as kBT divided by the volume of the container, negative pressure times A, where A is the area of the hole in square meters. So make sure that you're using the right units here. And also make sure that for pressure, you're using pascals. It's very particular about which units we're using for this problem. 2 pi mkBT to the 1/2 power, okay? So this is describing how the pressure is going to be changing with time. And in fact, like what you might expect, as time goes on, the pressure is going to go down, down, down within the container, but it's not going to go down at a steady rate. It's going to go down fast at first, and then as the pressure gets closer and closer to zero, it's going to even out. So there's our pressure inside of our container. But it might be more convenient not to deal with a derivative of the pressure, but actually calculate the pressure at any given time. And so what that pressure will equal is P0, which is the starting pressure. So the pressure at time 0, and then we've got exponent, or remember, e raised to the power of negative a t. T is the time elapsed since the hole was punctured, divided by v. And then inside here, kBt over 2 pi m to the 1/2 power. And there it is. So if we had, say, a spacecraft that was punctured by an asteroid and we knew the size of the hole, we could figure out how much pressure is going to remain after 30 seconds in the spacecraft. Like, that's just one example for how this technique was used. It was also used for a very interesting purpose during the Manhattan Project to isolate isotopes of uranium, because different isotopes of uranium have different masses, and so the lighter form of uranium, which is the more useful one, will effuse out faster. Now, finally, we're going to consider collisions in a system of gas particles. Now, any discussion of collision within a gas requires the molecular cross-section, okay? And what that represents, it's actually an area. So it's going to be in units of meters squared, most likely. And it represents the area that if a particle is flying through space, what is the area of the circle that another particle can't be in order for the two to miss each other. So see, I'm drawing other particles. Those two are far enough away that they wouldn't collide, but oh, see right there? The two particles are going to collide. So therefore, that area in which particles would collide is a cross section. It's called the cross section, okay? So how exactly do we calculate this cross section? Well, over here, they have a number of radii of different gas particles, and then over here, they have the molecular cross section. Unfortunately, this one's in nanometers, so you would need to convert to meters. But the way that it's calculated, the molecular cross section, by the way, uses a lowercase sigma symbol, and it equals pi times the radius of the central particle and the radius of the other particle that's running into it. If this is a pure gas, then both R1 and R2 are going to be the same number, and then you square that, okay? So that's going to be the cross section. Maybe you can see the formula for the area of a circle. So now that we know about the cross section, we can ask some other questions, like how frequently do particles collide? So that number is Z11, called the particle collision frequency. So that means for a given amount of time, how many times will another particle run into a given particle? You can find the formula in the book, but I'll just go ahead and write it down for you. The frequency of another particle running into any given particle is going to be the pressure in the system times Avogadro's number divided by RT, the cross section, square root of 2, 8 RT over pi m to the 1/2 power. So as you can see, the average velocity gets worked into this particle collision frequency. So now we can ask for a different frequency, which is the total collision frequency. How many collisions are occurring in the entire system total? This one equals 1 over the square root of 2, pressure of the system, Avogadro's number, RT, squared, cross section, and then once again this average speed. So those are two formulas that we can use to calculate particle collision frequencies. Now the last thing to talk about is the so-called mean free path. What that means is if we have a particle, we'll make it blue here, and that particle is moving through space, then it's likely that it's going to encounter other particles and collide off of it. So there we go. We just had a collision and then it goes off in this direction and then maybe it collides with yet another particle and bounces off that and keeps colliding on and on and on, kind of in a random pathway like that. The mean free path is how far it goes between collisions. See, the title says it's the average distance that a particle travels between collisions. And the symbol that we use to represent the mean free path is lambda. And it's going to be in units of meters. It tells us how far the particle is going between collisions, okay? And this is going to equal the average speed divided by the particle collision frequency. And we can just write down those quantities from what we already know. This just becomes RT divided by pressure, Avogadro's number, 1 over the square root of 2 times the cross section. The cross section is not inside that radical. By the way, it's worth noting real quick that in order for the effusion to be valid, this mean free path needs to be larger than the diameter of the hole through which the effusion is occurring.